Dear all, welcome. So let us move on to the second part of the module, electromagnetic waves. We start with the Ampere Circuit Law, and slowly we will discuss about the Faraday's Law of electromagnetic induction, and then we will end up with the Maxwell's equation. So to begin with the Ampere Circuit Law, that is the line of integral of magnetic field. The definition is the line of integral of magnetic field B vector around some closed loop will be equal to the mu naught times the algebraic sum of the current which passes through the loop. So let us understand the definition through some example. We will consider a long thin wire carrying a steady current I, and we will consider a small element dl of the magnetic field, and let us see what happens according to the Ampere circuit law. So as per the statement, we will have a thin wire which carries the current I, and whenever we have a steady current across a thin wire, we will have a closed loop of magnetic field will be generated. So we have B, which is actually the closed loop, and both the current and magnetic field will be perpendicular to each other. Now in this magnetic field, we will consider a small element, that is dl, and this magnetic field will have the loop area, with the radius small r. So for this condition, the Ampere circuit law states that the overall magnetic flux density integral of B vector into dl, B vector into dl is equal to the mu naught times the algebraic sum of current. So that is equal to the mu naught times the algebraic sum of current. So where mu naught will be the permeability of free space. So this Ampere circuit law actually correlates the relation between the applied current and the magnetic field generated. So now we will derive this equation 1 through some physics concepts, and let us start with the Biot-Savart law, which states that the magnetic flux density B at a distance r from the current carrying conductor at every point on the circle of radius r is given as magnetic flux density B is equal to mu naught by 2 pi I by r. So let us assume this as equation number 2. So this magnetic lines are actually all closed curve, and let us take the curve pattern, and in figure 1 we have considered a small element, that is dl, and the magnetic flux density B is along the direction of the element. Now the line integral around the closed curve is given as the following relation: integral of B cos theta dl, that is equal to integral of B vector into dl. Let us see this equation as number 3. If in case this theta will become 0, then we have cos theta, that is equal to 1. So this term will become 1, and equation 3 can be rewritten as integral B dl, that is equal to integral B vector into dl. We will have equation number 4. So now we have seen in the previous slide about the Biot-Savart law. We have found out the capital B, so that we will substitute it over here. So we have integral of mu naught by 2 pi I dl by r is equal to the right hand side term B vector into dl, or we will rewrite as mu naught by 2 pi I by r integral of dl, that is equal to integral of B vector dot dl. This dl is actually the surface area of the curve. So the surface area is actually 2 pi r, which we have studied in our lower class. So we will substitute this integral dl term, that is 2 pi r, in the above equation number 5. So we will have mu naught by 2 pi I by r as such into instead of this integral dl term, we will substitute as 2 pi r, that is equal to the right hand side term integral B vector dot dl. Finally, we will have the magnetic flux density, that is integral of capital B vector into dl, that is equal to mu naught I, by striking out the common terms, that is 2 pi and 2 pi. So this is defined as Ampere's circuit law. So the next topic is about the Faraday's law of electromagnetic induction. So this law states that, the first law states that whenever the number of magnetic lines of force, that we call it as magnetic flux, passing through the circuit changes, there will be an induced EMF developed across the circuit. So the second law states that the magnitude of the induced EMF will be directly proportional to the rate of change of magnetic flux through the circuit. And we'll explain the law over here. So the magnetic flux through the circuit will be given as pi 1, and the magnetic flux through the circuit after time t will be given as pi 2. So according to Faraday's second law, the induced EMF will be directly proportional to the difference between the magnetic flux, that is pi 2 minus pi 1, divided by the time t, or we will have induced EMF that is equal to small k pi 2 minus pi 1 divided by t. Let us have this as equation number 1, where k is actually the proportionality constant. In general, the proportionality constant for this equation 1 will be 1, and hence the induced EMF small e will be given as pi 2 minus pi 1 by t, or we will have induced EMF E is equal to d pi by dt Weber per second. So the next topic is about the Maxwell's equation. We will list out the 4 important Maxwell's equation, and we will find out the electromagnetic wave equation in free space, which form the foundation of classical electromagnetic theory. The equation describes how the electric and magnetic field are generated by the charges, the currents, and also the change in the respective field. So we will have some list of notations. So let us list out the notations which we are going to use in this equation. So the Maxwell's equation is actually a set of coupled partial differential equation which forms the foundation for classical electromagnetic theory. So this equation describes how a magnetic field and electric field are generated based on the charge, current, and also the change in the respective field. So before we start explaining about the Maxwell equation, we need to understand some notations which have been used to formulate these equations. So we have electric field E vector, magnetic field B vector, charge density, that is rho, we have electric current density, that is J vector, we have electric constant, that is permittivity of free space, epsilon naught, and we have 3-dimensional gradient operator del. So the Maxwell's first equation states that the product of del vector and electric field E vector is equal to the charge density divided by epsilon naught. This is the first equation of the Maxwell. So this law is nothing but the Gauss law in electrostatics. So this first equation explains the Gauss law in electrostatics, and since there is no time dependent variable, it is time independent. So this law denotes that the electric flux A vector depends on the charge density rho, and the Maxwell's second equation is actually defined as the product of del vector and magnetic field B vector, that is equal to 0. So this second equation states that the isolated magnetic field does not exist, and it explains the Gauss law in magnetostatics, and since there is no time variable, it is time independent. And this equation states that the magnetic flux, whether it's entering and leaving a given volume, will be equal. So we have Maxwell's third equation, that is the cross product of del vector and capital E vector, that is equal to minus dou B vector by dou T. So this will be the third equation of Maxwell's law. So it explains the relation between the electric field E vector and the magnetic field B vector. So we have the time variable over here. So this equation is actually time dependent, and this equation explains the Faraday's law and the Lenz's law of electromagnetic radiation. So we will have the fourth equation of Maxwell, that states that the cross product of del vector cross H vector is equal to the sum of J vector plus dou D vector by dou T, where capital H vector is actually the magnetizing field with electric displacement field, that is capital D vector, and the current density as capital J vector. So this law is actually time dependent since we have time variable, and this law explains the Ampere's circuit law. Now let us understand the Maxwell's electromagnetic wave equation for a free space. So for free space, the permittivity and the permeability are denoted as epsilon naught and mu naught respectively. So based on these notations, we will have capital B vector is equal to the product of mu naught and capital H vector. Similarly, we will have the other parameter, that is electric displacement field capital D vector is equal to epsilon naught into capital E vector. So let us assume these two equations as x and y respectively. So now let us try to solve the problem of Maxwell's electromagnetic wave equation in free space. So since there is no charge in free space, we will have rho that is equal to 0. So we will take the Maxwell's first law, which states that the dot product of del vector and E vector is equal to rho by epsilon naught. Since we have rho is equal to 0, we will have the product of del vector cross E vector is equal to 0. So we will assume this as equation number 3. Now let us take the Maxwell's third equation, which is given as the cross product of del vector and E vector, that is equal to minus of dou B vector by dou T. Let us consider this as equation number 4. Now the next step is, let us take a curl on both sides, that is the curl of del cross E is equal to the curl of dou B by dou T. We can rearrange the term in the right hand side, which gives you minus dou by dou T into del vector cross B, and using equation number x, we will have B vector is equal to mu naught H vector. We will substitute this B vector term, that is equation x, instead of the capital B vector over here. So that gives you the minus dou by dou T into del vector cross mu naught H vector. So thereby we will have del cross E vector is equal to minus mu naught dou by dou T del cross H. Now using vector calculus identity, we should have studied in our lower class, that is given as del cross E, that is equal to del into del cross del dot E minus del square E vector. So now we will rewrite this left hand side term as the following, but however we have found that the dot product of del vector and E vector is 0. So the second term of this equation will become 0, and hence we can rewrite as del cross E is equal to minus del square E vector. The second term becomes 0. So now we will substitute this equation number 6 in equation number 5 over here. So we will have minus del square E vector is equal to minus mu naught dou by dou T into del vector cross H vector. Let us assume this as equation number 7. So del vector cross H vector, we have already discussed about the Maxwell's fourth equation. So that is given as del vector cross H vector is equal to capital J vector plus dou capital D vector by dou T. So we will rewrite this term with the Maxwell's fourth equation. So we will have minus del square E vector is equal to minus mu naught dou by dou T into this following term, that is capital J vector plus dou T dou capital D vector by dou T. Since we know that capital J vector is 0 and also this capital D vector is equal to epsilon naught capital E vector from equation number y. So thereby the above equation can be remodified as minus del square E vector is equal to minus mu naught epsilon naught dou square E vector by dou T square. So equation number 8 is actually the electromagnetic wave equation in free space. So thank you all for your kind attention. Have a nice day.